And here we go. Hey, everyone. Yes, definitely happy Thursday, Eric. Um, all right, so I'll start with a little bit of administrative stuff. I'm emailing out tonight. This is something that I've just finished, so I have to type out all the emails. Normally, when I hand back the second exam, I put on top of it your exam average score, your homework average score, and your activity and quiz scores, the worksheet scores, and then I put where the grades are in the class. So I'm going to email what would have been on the cover of the second exam out to everyone. Now, there are some people that haven't, maybe have been having issues with the online exam, and I'm following up with those people. You'll see a couple emails go out. One's individually addressed with scores, and then one's addressed to the group in general. And that brings me through a point that's coming through here. If you are graduating or transferring at the end of the semester, the grade deadline is going to be May 13th. And so just let me know so we can plan around due dates and such. May 13th is the deadline for grades to be submitted in, normally at the end of the semester. So if you're looking at a transfer or you're looking at graduating and applying to graduate, we will need the grades in the grade book by then. And so that's a conversation we can have about, where we are with exams and things that we need to do. Everything, I am posting everything and all the due dates to be due by that point in time. But if you are not transferring and not graduating at the end of the semester, if you are coming back, we have some time that we can work out. We can file officially an incomplete, and we can extend the time on that incomplete into the summer a bit, so we can play catch up. And that's due to the nature of the things going on here. So we have some external pressure on due dates for that May 13th date, but we also have some external pressure that's making things harder to complete in the time period. And so depending on what you need to communicate with me so that we can arrange that. If you're still in program, you're still working on things, and you need time to get things done, we have that conversation. If you have somewhere you're going or you need that degree the end of this semester, that's where your plans are, then we'll have a different conversation about the due dates. So I just want people to know that, like, if you're freaking out because there's loads of stuff and access to things is all over the place, we can have conversations. Just because I have due dates down there doesn't mean that we can't be flexible. I've said in my emails I will be flexible, and we're working on things to get them done and get you the material you need to comprehend this stuff. So there's some conversations that might need to be had, and I'm filing those out with where we are on the grade book. I put things up on Blackboard's gradebook, but I don't have it calculate the grades. The way it weights grades has been a pain, and I was going to this summer work that out, but that's not affecting you directly now because that's something I have to do. All right, so that's that. Where we are at, so we are finishing section 4.5. I'm wrapping up all of section 4.5, and then we're going to look at section 4.6 in the second half of things. And I should say I'm wrapping up everything from section 4.1 to 4.5. It's a cohesive thing. 4.6 is an extension of that idea, and that's really going to wrap up chapter 4 for us. We're going to start looking at chapter 5. There are some things in the latter half of chapter 4 that get peppered into chapter 5 when we talk about function algebra. But for today, for the first half here, we're going to take all of these disparate rules that we had, and we're going to put them together. And we're going to look at them as building functions up from the roots and breaking functions down to the roots. So that is our goal of today, is to tie together all of what these seem to be disparaging things. So what I'm going to do here is I'm going to kind of look at what we have. If we start somewhere with a function in our descending order of power, right? This form I have been placing up here. And we learned that the leading coefficient, the a sub n and the a sub naught, are very powerful. They tell us some things that are happening. And so we want to use these forms to help us. But what we got to realize is there's some important things where n is the degree of our polynomial. And so that's the first piece of information that we get. And so, well, how do we organize this information? So the first thing we go to is the fundamental theorem of algebra. That says I have n zeros or roots if I include multiplicity. All right. So the number of answers I have has to equal the degree of the polynomial. But if the answer is repeated, that's the multiplicity, I can have, x equals 1 3 times. It can have a multiplicity of 3. That would still give me a third degree polynomial. In fact, I'll show that here. Right? If x equals 1, but it has a multiplicity of 3, then that would be that third degree polynomial. It would be x minus 1 cubed. And we would expand out all the terms and see what that looks like. But so the multiplicity. Now, underneath all of that, as part of the fundamental theorem of algebra, these involve complex numbers. All right, there are things we have that will not cross the x-axis. We saw that in our quadratics. And to do that, we had to have complex numbers. So we have a plus bi is going to be what these solutions are. If b is equal to 0, it is completely real. Like this solution. It's a completely real number. It's a complex number. It's 1 plus 0 imaginary parts. But all we really worry about is it being a real number. Oops. Let me. Now, if b doesn't equal 0, it has an imaginary part. Well, all of these coefficients were real numbers. And so if I am made up of things with imaginary parts, but I only see real numbers, something has to happen in the middle to get rid of those. And the only thing that really can happen, back in chapter 3 when we looked at complex numbers, is they had this thing called their conjugate. And when I multiplied this by its conjugate, I get, right, because I get a squared plus a squared times a minus bi plus a minus bi. So the middle terms canceled out. That was what the conjugate did. And then this last term is minus b squared I squared. But I squared is a negative number, so it turned this into an addition. And we looked at this in chapter 3 when we introduced imaginary and complex numbers had a conjugate. Well, if I am multiplying my complex number by its conjugate, I get all real solutions. Well, if all of these coefficients, all my a sub n's, all of this stuff up here, a sub n, a n minus 1 is real, but I have a complex root, then I also get its conjugate pair. So complex roots come in conjugate pairs. Now there are some interesting things that come out about because of this. If I have a third order polynomial, right? If conjugate roots come in pairs, I have to have a real result somewhere. It has to cross 0. And we saw that when we graphed these. Any odd function had to cross 0. And we looked at it in the multiplicities. If you need to move, if you had an odd multiplicity at that root, it crossed the x-axis. And so all of this information is kind of hidden in the fundamental theorem of algebra. So we use that to figure out what type of roots we're looking at. Well, we then augment that with Descartes' rule of signs. So I'll put together all the things we can do. Now, Descartes' rule of signs says if I look at the function and I count the sign changes, that is the number of positive real solutions. I'm just going to write it like that, positive real solutions. Counting down by 2. Yeah, that counting down by 2 thing is the thing. We've had some questions on that. I think Josh had some questions on that in the background, and we're going to explore some of those as we go through. So if I have a polynomial, right, and I start positive, I change sign once, I change signs a second time, then I'm going to have 2 or 0 positive reals. And the reason that we're counting down by 2 is that I might have complex numbers over there. And complex numbers come in pairs. So if I don't have the full number that is equal to my sign change, I might have a pair of complex numbers. And that's why we count down by 2. The other part of Descartes' rule of signs is I put in a negative for x, I count the sign changes, and that is the number of negative real solutions. So what these rules in scope are going to be letting us do is they're going to be letting us look at the degree of the polynomial and think of what the possible solutions could be. Right? We could have so many complex solutions and so many real solutions just by the degree of the polynomial. If it's odd, there's a possibility, not a possibility, there's definitely one real solution. If it's even, all the solutions could be complex with imaginary parts, or they could be a combination of complex and real, or they could all be real. Descartes' rule of signs lets me know how many possible positive reals and negative reals I have. And sometimes you get one sign change, which is telling you definitely have one of those things. So Descartes' rule of signs is very, very useful to ruling out the possibilities. Then we do the rational root test. We take all the factors of the leading coefficient, we're going to call that Q, and all the factors of the trailing coefficient, we call that P, and we look at all factors to make up P over Q. And what we know is these are our possible roots. These are possible roots. So we look at all possible roots, and what we go is, well, you know what? We'll use the remainder theorem. To test the roots. All right, and the remainder theorem said if x minus k is a factor, then f of k equals 0. Right? A factor will have a 0 remainder. We use the remainder rule to test this out. We drop it in. Well, what's nice is k is the 0. And so we test all those possible zeros. We test all those possible zeros, and we throw them into the function. And if we get 0, we're able to pull that out as a root. And then we use synthetic division to make our problem easier. Every time we get a root, we should divide it down to a lower order, because we have tools in our tool set that as soon as we get to quadratics, we can use the quadratic formula. And so there are things we can do once we get to quadratic. So wherever we're at, we want to work our way down. And so these are the ideas that I'm going to keep coming to, and we're going to run through a lot of examples. Today we're going to build functions up from the roots, and we're going to tear them back down to their roots. And we're going to look at examples that cover the gambit of the things that can happen here. And what I want to do is look at some tricks, too, that come about. And some things that can be done differently. There's an example I did in the book where I did it out the long way and divided it down, but there's also some tricks that we had from factoring that we can do it a different way. I think some of the problems in mathematics is that there's more than one way to do things, and when you're focusing on one technique, you sometimes won't look at the other techniques. And so I'm going to kind of think holistically about some of the things here. And the first thing I'm going to do is I want to show you a trick that works here, and this trick comes out of higher order polynomials. We're going to keep these rules in mind. I might scroll back up to them and talk about them, but we're going to always start with the fundamental theorem and what it's going to tell us about the solutions. Alright, switch over to yellow. So I'm going to look at a function. I'm going to have a polynomial on x where I have 4x to the fourth minus 5x squared minus 9. Now, I'm going to start with my fundamental theorem before I get to my trick here, and we're going to explore those tricks and see what we can do. And this trick is useful for more than just polynomials. This is probably, it's the thing we always do, right? You take the problem you have and you make it look like a problem you know how to solve. All of mathematics is based off of that to some extent. We just compile a lot of small little manipulations into a technique, or really big abstractions into a technique. But we're taking things that at the moment we don't know what to do with, and we make it look like things we've already solved. And this thing here looks really familiar to me. It has 3 terms, right? With coefficients in front of each term. It would be really nice if this was x squared and this was x, because then it would be quadratic, and I could jump right into the quadratic formula. I could use the quadratic formula to solve this out for me, and I'd be really happy with it. Well, if it would be nice if it looked like this and it was close to the same form, is there something I could do to make it look quadratic? And this is called substitution. And substitution gets used a lot in kind of the upper ends of algebra and above, as we start doing more and more things. Just solving for the unknown thing adds some complexity to it, so we need to kind of strip it down or change it. So the pattern that I want you to notice here is this and this, their powers. And this is always going to be the pattern running underneath this. We can do this with square roots, cube roots, different roots, but we want to look for a pattern in the powers. And so I'm going to write over here with capital letters the quadratic formula. Notice the power here. This power is twice this power. This power is twice this power. And so we're going to say, hey, this thing here is quadratic in form. The power of the middle term is half the power of the leading term. Or the power of the leading term is twice the power of the middle term. We have 3 terms, and the last term is a constant. That's the pattern we're looking at. So I'm going to say, well, I want this to be to the first power. So I'm going to introduce another variable. The one most math textbooks use is u equals x squared. I'm just going to say, hey, I don't like x being squared. It gets in my way. So I'm just going to make it u. Which means u squared is x squared squared, or x to the 4th. Oops, I'm sorry, u squared. U squared. I was trying to say it, didn't write it as much. Alright, we got it. So u squared is x squared squared, or x to the 4th. Well, look, we have these things here. So I can replace x to the 4th with u squared. So I can take this and I can say, hey, this is 4 u squared minus 5, well, this is x squared, so that's u, minus 9. So I've taken a 4th order polynomial that I could have found all my rational roots, I could have powered through it, and I said, you know what, I'm going to make this look like something else. I've made it look quadratic. Well, let's see what doing quadratic does for us. We've got the quadratic formula, and I'll write it in terms of u, which is going to say negative b plus or minus the square root of b squared minus 4ac over 2a. But in this form, a equals 4, b equals negative 5, and c equals negative 9. So I'll put all of that in here. Negative 5 is 5, plus or minus negative 5 squared is 25. Oops, why did my c not write out? 4ac, so a times c, 4 times 9 is negative 36, and negative 36 times negative 4 will be positive. So where is my calculator here? Over here. Still have not had a camera show up so that I can do the calculator stuff, and it's something I'm going to work on. So let's see, 4 times 4 times negative 9 is 144, right? And the negative will make that positive. All over 2a, which is 8. All right. Now, the quadratic formula is the least consistent, if not pretty, right? It's got a little bit of everything, additions, multiplications, and subtractions. So I shouldn't have chuckled at my own joke so much there. But it's consistent. It will always give us an answer. All right, we might have square roots and imaginary parts to it, but we get something. And the square root of this is 13, so I get 5 plus or minus 13 over 8. I'll do the plus part first. So 5 plus 13 is 18, and 18 over 8 is 9/4. That's the positive. Positive, I'll do the negative. 5 minus 13 is negative 8, and so negative 8 over 8 is negative 1. And so there are my two answers for u. But my initial problem was, what was x, not u? So I want to go back and use this definition of u to solve for x. So I will say 9/4, so x squared equals u, and I have a value of 9/4 for 1, and x squared equals negative 1, because u is that, and I had my two solutions. Alright, so I take the square root of both sides, and that'll give me plus or minus, well, the square root of this is 3/2. And I'll take the square root of both sides here, and I'll get plus or minus square root of negative 1, or I. And so all of my solutions for x are minus 3/2, plus 3/2, whoops, positive 3/2, minus I, and positive I. We don't really write our leading positive signs, so I'll do it like this. There we go. So, have we satisfied the fundamental theorem of algebra? Does this technique work? Is the substitution a good way of doing it? I think this is quicker. The key is you have to recognize that pattern. You have to recognize you have three terms, and that the power, the last one's a constant, and that the power is double, right? That's the pattern of quadratic in form. And whenever you have something where you've done a substitution, you don't stop here at your substituted thing. Your question was about x. And so you have to solve back for x. But that's okay. So, did we meet the fundamental theorem of algebra? It was a fourth degree polynomial. We have 4 solutions, right? And those 4 solutions, one of them was complex. So it included the complex conjugate. So we got this pair. The other thing to look at is if I were to do my rational root test, I would look at all the factors of 4 and all the factors of 9. And so all the factors of 4 would be in the denominator, and all the factors of 9. So I'll put my p is going to be plus or minus 1, plus or minus 3, plus or minus 9. My q is going to be plus or minus 1, plus or minus 2, plus or minus 4. Sorry. And I would make all the possible fractions of them, and notice plus or minus 3/2 sits there, and that was within our solution set. So this works. This does what it's labeled on the tin. It satisfies it. The steps work. The substitution saves us some effort. And so our job is to look for that pattern. And we will do substitution on and off. This is kind of the first place the substitution will come into play, is with polynomials. We will see with rational functions where we have a denominator that has values in it which are not polynomials. Polynomials can't have denominators, can't have x in the bottom. Or when we have square roots or roots, that this substitution idea works really, really well, and it helps us because the quadratic form is nice to go. Alright, so that's trick one. And notice how I keep referring all of our tests for polynomials. I'm going to keep doing that. Alright, I'm going to switch over to bright yellow. Blue. I'll go to bright blue. Now this one I had done in class last Thursday. Whoops. And I want to review it, doing something the book did, which I think is neat and of good value. This is a pattern again. And the pattern we're going to kind of go here is, well, it'd be really, really nice if I could factor this stuff. Whoops, this first one's a cubed. Let me make that a cubed. My apologies. And if there was a good factor or a good grouping factor in this, I could simplify this by factoring. And so the thing to look for is that in the numeric terms, especially with the constant, one of these has a nice multiple of this. And so we're going to factor by grouping. Remember when we do the AC method, we could group down the middle? So I'm going to pretend that this polynomial has an imaginary line dividing it into 2 bits. And I'm going to work on this bit here. This has an x squared term, and this has an x squared term. So I can pull out x squared, and that leaves an x plus 2. Now I'm going to pop over to the other side here, and this has a 4, and this can be divided by 4. So I'm going to pull out the 4, and that leaves behind an x plus 2. So let me get rid of the yellow line a bit here, since my division down the middle doesn't need to go as far. Get my eraser out. There we go. Those are my 2 factors, right? If I factor out the x plus 2, I'm left with the middle x squared plus 4. And these are my 2 factors of the polynomial by factoring by grouping. Well, that tells me one of the roots is negative 2. And the other roots is plus or minus 2i. Right, because the square root of a negative is imaginary, and this is 2. Well, doesn't meet the fundamental theorem of algebra. So, looking at this, my n was 3. It's odd. I have to have at least one real result. I'm going to have 3 answers. Well, there's one real result, and I have a complex result, and its complex conjugate. These are pretty much the quick shortcuts that we can get. Is it quadratic in form, and can we factor by grouping? After that, we have to use the full list of things we can do with our equations. We're going to have to use fundamental theorem, we're going to have to chart out Descartes' rule of signs, and then we're going to have to use the rational root test. So I want to do some of those from kind of a review packet I would have thrown out in class on a day like today. I'll walk through some of these review questions, and then I'll put up a short little thing addendum beside the homework, so you can get some points for it. But well, I'm going to look at that and what we can do using all of these rules, and then when I do, I think there were 2 or 3 of these. Then I'm going to do it in the other way, building functions up, using this information in reverse, as if we had data or solutions and we wanted to see what the question was behind it, what the function was behind it. Which are both very applicable things. Going in both directions is a fundamental part of how we do mathematics. So let's get here. Let's scroll up here. All right, so I'm gonna pop over here. Let me make sure. Yep. All right. So this is the worksheet I'm looking from, and what we're going to do is we're going to start with we're going to start with number 3, because number 3 is a nice use of the remainder theorem. So number 3 says if x plus 2 is a factor of 2 capital K x cubed plus 4x minus 8, then what is the value of K? Let's go over to the blackboard here and rewrite this. So if x plus 2 is a factor of, and I'll go f of x equals, I'll write it as a function, and we'll write the functional form 2 capital K x cubed 4 8. 2 4 8. 2 4 8. 2 capital K x cubed plus 4 x minus 8. What is capital K? What is going to be capital K? All right, so what we want to look for, or what do we want to have us help things out here, is going to be our remainder theorem. And specifically our remainder theorem as it has to deal with if something is a factor. So let me pop over here. Let's write down what this theorem is. It says if f of negative 2 should equal 0, right? Because our factor is x minus little k, and because this has a positive sign, it's saying our root is negative 2. That's the thing with these theorems when we're looking at the factor parts. When we turn them into roots, they change sign on us. And that's because we're saying, hey, x equals negative 2. Well, if I solve x plus 2, add 2 to each side, I get that. And it was the ability to multiply many things together to equal 0 that let us split things apart into factors. So when I talk about the 0 or the solution or the root, I'm talking about x equals a number. If I'm talking about the factor, I'm talking about x plus or minus a number. But that number comes from the solution or the root. And when I switch between the two, the sign changes on us. And so in this case, this is the factor, but into the function goes the root. That's the factor, into the function goes the root. That's also why when we did synthetic division, it got a negative sign, because synthetic division was relying upon the root, or the 0, or the solution, right? Multiple words for the same things. All right, so this isn't too bad, because I have x minus 2, so I can put minus 2 in wherever I see x. But this should also equal 0. So I'm able to turn it into an equation. And that equation now only has one variable, capital K. So we're applying our remainder theorem here to find out something about a missing coefficient. This type of manipulation, it's slightly artificial, but manipulating your coefficients versus your variables is something else that does happen with data. And so some of these manipulations help us get used to what our functions are doing. And I've always liked this problem because it illustrates the remainder theorem rather well. In fact, when I first did this problem, I did it using long division. And got a remainder that I then set equal to 0, because I had never been really taught the remainder theorem. And so when I learned the remainder theorem and went back to this problem, I was surprised at how quickly it solves comparatively. So -2 to the third is -8. I'm just going to keep that in parentheses. I want to move my big K to the right here. I'll put the 2 out front. 4 times -2 is -8. And -8 equals 0. Alright, so I'm just going to clean this up a bit here. 2 times -8 is -16. And -8 and -8 is -16. Whoops, this equal sign in the front I don't need. I'm sorry. I was getting all excited. Let me grab my eraser here. So let's see, that's 2. And that's -16. That's better. Alright, well, I'm going to add 16 to both sides. And then I'm going to divide by -16. And I found my coefficient in this case is going to be -1. Alright, so our remainder theorem is useful in this type of problem. Again, I'm doing examples around all of the little bits we've used, right? So I've used a substitution to reduce a fourth order to a quadratic, and then use the quadratic to solve the solutions. Keeping the fundamental theorem of algebra with us so that we knew that we had to collect together 4 solutions, and if there was a complex solution, it needed to come in a conjugate pair. Right? So we're touching all these rules you learned over these 5 sections. Right, and we're going to continue. We're going to wrap them in little packages as they relate to these problems. Second thing we did, I took a third order polynomial and I used grouping to put it into 2 factors. Those factors I set equal to 0, and I solved. One gave me an imaginary conjugate pair, and the other one gave me a real solution. Here, I just focused on the remainder theorem and what we could do with the remainder theorem. Alright, let's look at some things we can do with finding zeros. So we're going to look at number 9. Find the zeros of the polynomial 2x to the 4th minus x cubed plus x squared minus x minus 1 if I know that I is one of them. Alright, I'm going to write this down now on the blackboard here. Oh, this didn't switch over to the browser. Let me switch over to the browser. I'll repeat this here. We're going to do number 9 here. So we're going to find the zeros of the polynomial. Px equals 2x to the 4th minus x cubed plus x squared minus x minus 1 if we know I is one of them. Alright, let me write that here. Any suggestions for color? I'm in the mood for the neon purple. Go with a big 80s feel on it here. So my function f of x is equal to two x to the fourth minus x cubed plus x squared minus x minus 1. And I know one of my solutions, x, is equal to I. Alright, so we're going to start. Right off, we'll look at the fundamental theorem of algebra. I have a fourth degree polynomial because my highest power is 4. So n equals 4. So I have 4 solutions, or roots or zeros, depending on their multiplicities. Ah, the pen size changed. Just trying to figure out why it was writing really thin. We'll see how we go here. Now, the other part of this fundamental theorem of algebra says they're going to be complex numbers. But because all of my coefficients were real numbers, right? There's no imaginary numbers in these coefficients. That's a positive real, that's a negative real, that's a positive real, and so on. They're real numbers. So I have to have the complex conjugate of this, which is negative I. So I went from having one root needing 3 to now I have 2 roots and I only need 2. Well, if I only need 2, I want to reduce this fourth order polynomial. I want to reduce it to a quadratic. How can I do that? I need to divide this by something. Well, let's put these together. So if I turn these into their factors, that's x minus I as a factor, and that's x plus I as a factor. Well, these two things were multiplied together, so I'm going to do that. So first terms gives me x squared. The outers gives me positive ix, but the inners give me negative ix, so that middle term cancels out. Right? That's the job of the complex conjugate, is to cancel out that middle term. Actually, to cancel out all imaginaries, as we'll see. It's not always just the middle term. And then the last term is going to give me negative I squared. But I squared is negative 1, so that's x squared plus 1. So this conjugate pair was the same as having x squared plus 1 as a factor. Well, if this is also a factor, I can divide this by this. And so I get to pull out my polynomial long division, right? That thing we did in section 3, where we did polynomial long division. Note, please note. And there's two ways to look at that. X is squared, so we can't use synthetic. Or we can say, hey, you know what? It isn't a root, right? We're not dividing by a root, so we can't use synthetic. We're saying the same thing. So let me set up my long division here. So I'm going to set it up and then scroll down for it because, well, it is long division. And so we need to have some space. Something about where my hand is there. Keep raising and lowering when I write across that way. And we're going to divide it by x squared plus 1. So I make sure my powers are descending and that I have a place for each power in this part, and now I'll scroll up. Alright, so x squared, looking at the leading coefficient, goes in x to the fourth, 2x to the fourth, 2x squared times. Right? This leading coefficient divided by this leading coefficient gives me this. Now I'm going to multiply that back through. 2x squared times x squared is 2x to the fourth. Multiply it back through, I get plus 2x squared. I'm going to change my signs. So this becomes negative, this becomes negative. And I'm going to add. So the negative x cubed comes down. This is going to give me negative x squared. And these other terms fall in place. I look at my new leading coefficient, negative x cubed divided by x squared is negative x. I multiply across. Negative x times negative x squared is negative x cubed. Negative x times 1 is negative x. I change my signs. And I bring everything down. And again, if I did my job right, this first term cancels. I get negative x squared minus 1, because these two terms cancel. Alright, so this is my new leading coefficient. I look at my previous leading coefficient. Negative x squared divided by x squared is negative 1. I multiply back through. I get negative x squared minus 1. I change my signs. And look, a remainder of 0. I should have gotten a remainder of 0 because I knew this was a factor, but look what I've done. I've reduced my polynomial to this. So I'll switch colors one more time. 2x squared minus x minus 1. So I have x squared plus 1 as one factor, and I have 2x squared minus x plus minus 1. Well, I know I need 4 answers, and I know this one gives me x equals I and x equals negative I. So I need answers to this. But it's second degree, right? And that was what we did in chapter 3, all of the quadratics. So I can say, for this other part, x equals minus b plus or minus the square root of b squared minus 4ac over 2a. And a is equal to 2, b is equal to negative 1, and c is equal to negative 1. So this becomes 1 plus or minus 1 4ac 8 plus 8 over 4. And so this becomes 1 plus or minus the square root of 9 over 4. Or 1 plus or minus 3 over 4. I'll do the positive ones first. That gives me 4 over 4, so that's 1. I'll do the negative next. That gives me negative 2 over 4, or negative 1/2. And I now have my 4 solutions. So our fundamental theorem of algebra helped us out. We knew one of them was a complex conjugate, so we expanded that back out and divided to simplify the terms. Alright, I think I don't have enough blackboard space there, so I'm going to save this out. Oops, dropped my pen. I'll get that in a second. And I'm going to clear this off. So, oops. Give me a second here. All right, this is me vigorously erasing the board. What is today? April 16th, evening, part 1. There we go. That's in a good place. Reopen the other one. All right. All right. So we're going to look at 2 more of these, and then we'll start building some things up. Let me switch this over here. Come across. Now 1 more of these. We'll do number 6 here. All right, number 6, we have no idea what the roots are. We have nothing to go by, so we're going to have to use all of our rules on this 3rd degree polynomial. All right. So we have t of x equals 8x cubed minus 14x squared minus 5x plus 2. Let's get t of x over here. So t of x, and give the function a different name for a bit. 8x cubed minus 14x squared. 8x cubed minus 14x squared minus 5x plus 2. All right, let's review all of what could be going on for us here. So we start with the fundamental theorem of algebra. And this is to the 3rd power as the highest one. So this is degree 3. Now, before I dive in and do anything else, I want to kind of get an idea of what I have with degree 3. So my complex numbers come in 2s, and my real numbers can come in any amount. So I could have 2 complex and 1 real, or I could have 0 complex and 3 real. Okay. Those are going to be my possibilities. Be nice if I could figure out a little bit more. So we'll run over to Descartes' rule of signs. So t of x, if I go through and I count the sign changes, positive to negative, that's 1 sign change, stayed negative, back to positive, so there are 2 sign changes. So this has 2 or 0, because I count down by 2, positive real solutions. So by having 2 sign changes in the positive value, at most I'm going to have 2 positive real solutions. At most. But because there might be complex numbers in the background, I count down by 2. Means I could actually have 0 real solutions. 0 positive real solutions. All right, well, let's look at the negative. So if I put negative x in there, that's going to change this to, well, a negative cubed is negative. A negative squared is positive, so it doesn't change the sign there. All right, so if I put a negative in here, it'll change the sign. If I put a negative in here because it's squared, it won't change the sign. If I put a negative in here, it changes this sign. Let's count my sign changes. I haven't changed 1. So this has 1 sign change. And so this has 1. Well, if I count down by 2, I'm not going to get 0. So this has 1 negative real root. Guaranteed. I have something guaranteed. So my options now, if I bring this down and I expand it, I have my complex roots, my positive reals, and my negative reals. So if I have 2 complex solutions and my guaranteed 1 negative, I have no room for any of the positive reals. So I get 0. Right? Because this has to add up to 3. I'm only allowed 3 solutions because of my fundamental theorem of algebra. Okay, well, if I can't have 2 complex, I have to have 0. And this says I have exactly 1 negative. So I have to have 2 reals. 2 positive reals, sorry. So notice, I hope in this chart, because of the complex always taking 2, you can see why these count down by 2. And so I only have 2 options here. I'm going to have 2 complex solutions and 1 negative real solution. Or I'm going to have 2 positive real solutions and 1 negative real solution. And so I go to myself, you know what would be really nice? I'm guaranteed to have this. So let's look for that first. So I'm going to come here. This is my A sub naught, so I'm going to rewrite the whole thing here because we're going to have to scroll. I'd pay good money right now for something that would let me have multiple windows that I could stream out to you, that you could choose between the windows, like having 4 blackboards up and you could look at the one you wanted to look at instead of me scrolling up and down. But and when I mean good money, right? I'm on a teacher's salary, so that's like $1.50, right? Alright, so there is my function. So what we have to do now is we have to use the rational root test. I have to look at all of my factors of A sub naught and all of my factors of A sub n. Right? Remember, the leading coefficient and the constant are the things that are going to tell us so much of what's going on. They're going to help derive everything for us. And so what we want to do here is we want to look at all the possible factors. Well, what's nice is for A sub naught, we have plus or minus 1 and plus or minus 2. Because it is 2, it only has 2 factors. So we don't have as much to play around with there. But for A sub n, we have plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Alright, so there we have all our possible P's and Q's. And what did I say? We mind our P's and Q's, right? And that we have the P's and Q's as a way of finding our possible roots. And so our P's are made up of the A sub naughts, and our Q's are made up of the A sub n's. And so what we want to do is I'll say, hey, that's P and that's Q. So all of our possible rational roots are all possible P over Q's. So I'll work my way through each Q. So I'll start with 1 on the bottom. 1 over 1 is plus or minus 1. 2 over 1 is plus or minus 2. That's not too bad. I'll move over to 2 now. 1 over 2 is plus or minus 1/2. Right? 2 over 2, well, that's plus or minus 1, and I already have that, so I'm not going to write that down again. So I've done these as my denominators. Now I'm going to do 4. So I get 1 over 4, so that's plus or minus 1/4. And I get 2 over 4, which reduces to plus or minus 1/2, but I already have that. Yeah, this is not too bad. It's working our way through everything possible nicely. And now I'll use 8 as a denominator, so 1 over 8 is plus or minus 1/8. And 2 over 8, which reduces to 1/4, but I already have that. So 1, 2, 3, 4, 5, 10 possible rational roots. I have 10 possible rational roots, but I am guaranteed one of them's negative. So I'm going to focus on the negatives. And I'm going to use my remainder theorem. So I'm going to look at t of -1 or -2. I'll start with my smallest number, and I'll work my way up. So I'll go 2, -1, -1/2, -1/4, -1/8, right? I'll get closer and closer to 0 to see what's going on. So I'm going to take -2 and I'm going to drop it in for each x here. I'm going to do this on the calculator. So I'm going to have 8 times -2 cubed minus 14 times, and I'm putting all these -2's in parentheses because I'm just going to scroll back up and change them to -1. -2 squared minus 5 times -2 plus 2. And I put all those in and I get -108. I'm going to try to sound old here. Back in my day when I first learned these, we had to do them all by hand. We didn't have calculators to help us do this, right? And this is when I walked 58 miles in the snow to go to school. No. I was actually very lucky is when I first started learning algebra, I think my first year of algebra, we weren't allowed calculators in class. And then when I got into trig, that's when the first trig calculators started coming out, mid-80s. The cheap ones. They were like before that, engineers could get a good calculator for about $400 or $500. But outside of that, schools still taught with slide rules. But in the 80s, the really cheap trig calculators, kind of like the TI-30s, came out. And so I only had a semester or a year, like 7th grade or 8th grade algebra, where I had to do any of this stuff by hand. When I did it a little bit later, we still did some of the graphing stuff by hand because graphing calculators were still a little bit out of the price point of everyone. Still are now, really, in my opinion. But so what's nice about this is I've done this once. I've entered it on my calculator once. I just up arrow. I come back in and I replace -2 inside all those parentheses with -1. Right? And I have to do a page full of calculations to get where this is going. I just use my calculator to repeat. Up arrow, change all the -2's to -1, and this gets me -15. Now, the intermediate value theorem tells me that my function is going to touch every value in between these things. So if I don't find a root, but this number changes over to positive, I know I have a real number in there that's not a fraction, like a pi or something like this coming across. So what's nice is I can watch this go down. As it goes down, I'm getting closer and closer to 0. So I know I'm moving in the right direction. So I'll go, what did I say next? I'm getting closer to 0, so I'll try -1/2. Again, up arrow on the calculator. And I'll put in 1/2. Whoops. There we go, 1/2. Half. Got my squared term. Now I just need to get my x to the first term. I think I'm good there. And lo and behold, I've got a 0. That went a little bit quicker than I expected. No, I did this one before. In fact, the other time I did it, I tried to go from 1/8 upwards. 1/8, 1/4, 1/2. And I accidentally skipped 1/8 and it was right to it. But this is good. It's there. We have a 0. And I know none of the other negatives are going to be it because Descartes' rule of signs told me I only had one negative root. So I have one answer. X equals negative 1/2, or that's a factor of x plus 1/2. Well, what I'm going to do now is I have two options. I can go through in my calculator and I can test every one of these positive ones to see which ones are 0. Or I can divide this. And I'm going to use synthetic division to reduce the complexity of this problem. So I'm going to take my negative 1/2, which is what I'm going to, which was my root. That's going to become my synthetic division. And I'll take my coefficients of my t of x. So I'm up here, I'm taking all of these coefficients, and I'm taking the root that I found. So I use synthetic division. And this is where synthetic division is really nice. It goes quickly for this. So I take down 8. I multiply 8 by negative 1/2. I get negative 4. I'll add these two, I get negative 18. A negative times a negative is a positive. 18 times a half is 9. Negative 5 and positive 9 is positive 4. Negative 1/2 times 4 is negative 2. And the remainder should have been 0 because this was a root. And so x equals negative 1/2, or that's saying I have a factor plus 1/2. But my other part is 8x squared minus 18x plus 4. And you think to yourself, well, what can we do here? I've reduced it down to a second order. So x equals minus b plus or minus b squared minus 4ac over 2a. So that's 18 plus or minus 18 squared minus 4, what's 4ac? There's c and a, so 4 times 32. All right. 4 times 4 times 8, which is 128. All over 2a, which is 16. Whew. Nasty looking. What is 18 squared? 324. All right. So I'm going to do the whole discriminant, which is the thing in the square root. 18 squared minus 128 is 196. Again, I'm running to my calculator here, and you should be doing the same thing. You should be having your calculator handy for these type of things, especially when the quadratic equation comes up, because what we need to do is keep track of where things are going in the quadratic equation. All right, well, 18 plus or minus the square root of 196 is 14 over 16. So I'll do the additions first. 18 plus 14 is 32. And this is the additions first. So 32 sixteenths is 1/2. And then the subtraction, 18 minus 14 is 4, or 4/16, which equals 1/4. And lo and behold, those were possible roots. And so all of my solutions are x equals negative 1/2, positive 1/2, and positive 1/4. All right, so that is what all of the sections 1 through 5 did for us. They gave us the ability to deconstruct these things using the fundamental theorem of algebra, and they let us find roots from these amorphous things coming across. All right, what I'm going to do here is we're going to take about a half hour, right? We'll say we'll start around 7:40, and I'm going to come back in and we're going to look at just some small things on building up, and then we'll look at rational functions also, what it means to have a function with division. So I'll send out a new stream, about 2 minutes here, 3 minutes here, and how about we say we'll aim for around 7:40, right? It's not quite 7:20 yet, so it will take 20 minutes. Everyone can go to the restroom, grab some chips or something, and then we'll come back.